Alright, so sorry about getting cut off in that last video, but what I was saying is that the new pressure at 4 meters is 1.3 times the pressure at 1 meter. I would also like to note here, and this is going to be a really important note, that pressure in pascals does not equal force in newtons. And so please, please, please don't get those confused. If I want to find the force due to pressure, I can do that force equals the pressure that I find from this type of equation times the area of whatever liquid or whatever volume that I have. And so know that if I'm looking for force in newtons, that does depend on the area above me. Okay? And so moving on, this has some pretty neat implications for pressure. And so when you're diving, right, you start with an initial volume, a lung volume at the top of the water. And then as you go down, 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 your lungs actually compress and decrease in volume due to the pressure. This also leads to a what can either be fun or dangerous thing when you're diving and coming up. And so if you're a little diver down at the bottom and your lungs are compressed, there is still the same amount of air in them, but it's taking up a smaller volume. If you hold your breath and ascend, right, your lungs are going to expand because of the decreasing pressure as you're ascending. Unfortunately, this can be really dangerous if you hold your breath and ascend. You can actually lead to lung overexpansion, which is a life-threatening condition. However, if you're a safe diver, there's this really cool thing that can happen. And so if you're at depth and you're ascending, what can happen is you can exhale all the way up. And so you can exhale over the course of 100, 80, 60 meters, whatever it may be that you're diving at. You can exhale the whole way up, which is a pretty cool feeling because your lung volume is continually expanding. You're never going to run out of air if you're exhaling slowly going up. If you do exhale, right, and you run out of air somewhere in the middle, then you're in trouble, right? And so that's why it's important to exhale slowly. When we calculate the pressure of water at rest, this is what we call a hydrostatic pressure. And so in our situations where we've been talking about, water in some kind of a cylinder, that water is at rest. It's not flowing. And so these calculations that we've been doing of pressure equals initial pressure plus the density of the fluid, gravity, and the depth, that's a hydrostatic pressure, and that's considering that that object or that fluid is not moving. In something like an ocean, obviously, this is not true, and we'll get to that later in the chapter. But there's also this really cool thing, right, is that if I have a system where water is connected, water at the same depth within that system, no matter the area of these two, is going to have the same pressure. And so water at the surface is going to have a pressure of 1 atmosphere, right? Or that value of kilopascals that we've been talking about, same thing. If I go down to a certain depth, the pressure is going to be the same across, right? If I'm down at the bottom of the container, the pressure is going to be the same across. Now, the force might be different because of the area over the top of it, but the pressure is going to be the same. And this will come in helpful here in a minute. And so this is a very bad picture, but basically I've got all of these containers, container A, B, C, D, and E. They're all different shapes. They might have different volumes of liquid within them, but they're all the same depth, right? And so what I want to know is arrange these in order of pressure at the bottom, right? And so arrange these from greatest pressure at the bottom to least pressure at the bottom, and I'm going to give you a minute to do that. And you're welcome to pause the video, spoiler alert, but all of these have the same pressure at the bottom because all of these are water, or presumably the same fluid, and they are all at the same depth, right? Below the surface, and so you're going to experience the same pressure at the bottom. Again, force may be different because what we're looking at is the area over when we deal with force, and so but the pressure will be the same. So what I want you to do is pause the video and go ahead and try number 9 and 11 in your book on page 434. I'm going to go on and work out the examples so that after you've done it on your own, you can start playing the video again, work along with me, and check your work. Right? And so on page 434, number 9, all right, I see the question. Part A is asking what volume of water has the same mass at 8 cubic meters of ethyl alcohol. And so for part A, right, I know that the density of a liquid is equal to mass divided by volume. And if I'm talking about ethyl alcohol, I can look over in that table in the book, and I know that it has a density of 790 kilograms per meter cubed, right? Oop, cubed, there we go. And so when I come down here, I can just plug in. I've got 790 kilograms per meter cubed for the density of ethyl alcohol. And it's asking me, let's see, it's given me meters cubed, which is a volume, so I don't know the mass of that yet. But I do know the volume, which is 8 meters cubed. When I solve out for the math, I'm going to multiply both sides by 8, and I'm going to get that the mass of that is equal to 6,320 kilograms, right? And so I found my mass first. The next thing that I've got to do is it's asking me, okay, well, what volume of water has that same mass? And so I'm going to come down here and I'm going to be talking about H2O, and this was about ethyl alcohol, right? ETOH. And so with H2O, same thing applies, it's mass divided by volume. I know the density of water is 1,000 kilograms per meter cubed. This time I now know the mass and I've got to find the volume. So I'm going to plug that mass in here, 6,320 kilograms per, well, I don't know what volume. When I solve, what I do is I multiply both sides by V, right? On this side they're going to cancel and I get 1,000 V over here. And then I divide by 1,000, okay? And when I get V, it's going to be 6,320 kilograms divided by 1,000 kilograms per meters cubed, which is going to give me a volume of 6.32 cubic meters, right? And that should be my final answer for A. That is the volume of water that has the same mass as 8 cubic meters of ethyl alcohol. And then I'm going to move on to part B, and it says, if this volume of water completely fills a cubic tank, what is the pressure at the bottom? And so when I'm looking at a cubic tank, right, it means that all sides have the same value, and I know whatever that is equal to 6.32 meters. And so to find the depth of this, which is what I need, I'm going to take the cube root of 6.32, and I can either do that as a cube root function, or I can do 6.32 to the 1/3 power. It's the same thing. And that's going to give me the height of that container so I can figure out the depth. When I do take the cubic root, I get that as equal to 1.85 meters. And you can double check that. 1.85 cubed should give you 6.32 cubic meters for the volume of that, but I'm going to use this as going to be equal to my depth. And then I can go back to that pressure formula that we know. The pressure that we experience is equal to the initial pressure plus the density of the fluid, gravitational constant, and the depth. When I work that out, I start out, I'm going to assume it's sea level with 101,300 pascals, plus the density of water is 1,000 kilograms per meter cubed. Gravity is always 9.8, and the depth I now know is 1.85 meters. Right? When I do those calculations, I'm going to get a pressure of 1.19 for e to the fifth pascals. Right? And so if you got this, great job. That was a really, really intensive problem. And if you got that, very, very good job. All right. And so moving on to number 11, a 35 centimeter tall, 5 centimeter diameter cylindrical beaker is filled to the brim with water. What is the downward force of the water at the bottom of the beaker? And so I know, right, I'm not just talking about pressure. Force equals pressure times the area. And so when I'm looking at a cylindrical beaker, right, I've got a 5 centimeter, which is going to be, I'm just going to go ahead and put that in meters, 0.5 meter diameter radius, right? And I know the whole thing has a height of 0.35 meters, right? And so the area is going to be the area of the circle because that's what's going to be pushing down. However, I got to find pressure first, and so pressure equals P naught plus the density, gravity, and depth, right? Which is going to give me 101,300 plus 1,000 for water, 9.8 for gravity, and 0.35 meters for the depth of that container, right? Because that's what's going downward. That should give me a pressure of 104,730 pascals. Right? And so now I can take this pressure and talk about that in terms of force. So force equals pressure times area. I'm just going to plug that value in here. And so I get 104,730. Right? And then my area is going to be this area of the circle, which is pi r squared. So I'm going to do pi times 0.05 squared, which should all give me a final force of 210 newtons. And so if you got that as your answer, again, excellent job. You did it right. And so the bad thing here is that I kind of lied to you earlier when I said that we measure pressure in pascals. Pressure sucks in a way because I measure it in a lot of different things and depending on the use. Pascals is just the SI unit of pressure, and so when I'm asking you questions, I want your unit in pascals. And so here's a table, it's also in your book, that talks about all of the different units we use for pressure. And it's just the same thing. And the typical unit in use is atmospheres. Atmospheres refers to the atmospheric pressure, and that's the typical unit because we live in the atmosphere, and that's usually what we're concerned with. But here are all your conversion factors. So we've already talked about pascals, right? The abbreviation is PA. And these are your conversion factors to equal 1 atmosphere. So there's 101.3 kilopascals per 1 atmosphere. And remember, this value was at sea level. And so the other way that we can begin to think about this is at sea level, I also have a pressure of 1 atmosphere, and that makes a lot more sense. It's a lot more intuitive than 101.3 kilopascals. Conversely, we can also talk about pressure in terms of milliliters of mercury. And so milliliters of mercury, and mercury in general, inches of mercury as well. Mercury is typically used when we're talking about weather and measuring pressure with weather devices. And so, as with all things, the U.S. tends to make things more complicated. We like inches of mercury. The rest of the world is using milliliters of mercury. And so